In this lecture, we will talk about biological forms of renewable energy, showing where they fit in the U.S. energy portfolio and in terms of energy return on investment. We will describe several sources of bioenergy and talk about the advantages and challenges of each. This week, we will be focusing on the 11% of the U.S. energy consumption that is fueled by renewable energy resources. Of those renewable sources, biomass makes up the largest share of our energy, followed by wind, hydroelectric, solar, and finally geothermal. While the renewable share of U.S. energy consumption is fairly small today, it is increasing and it will be super important as the world transitions to a post-fossil fuel economy. When we talked about fossil fuels, we defined the term energy return on investment, or EROI. EROI quantifies the amount of energy you get out relative to what you put into extracting, refining, and distributing the energy source. Remember that if EROI is less than 1, then it takes more energy than you get out. And if EROI is less than 3, the source may be minimally useful over extended periods. These tables compare the EROI for various fossil fuels versus nuclear power and renewable energy sources. Big takeaways from this table are that many renewable energy sources already have EROI that is comparable to most fossil fuels. Also, as we invest in technology for renewable energy, experts expect EROI to increase. Conversely, as we deplete the easiest types of fossil fuel, we expect their EROI to decrease over time. Biofuels and related forms of energy are derived from biological material, typically plants. The US and Brazil are the world's largest producers of biofuels. We will lump together several different types of biologically based fuels, but they have important distinctions. Wood burning has been used as an energy source for thousands of years to heat homes, like the pellet stove shown here. And today, most electricity generation from wood biomass in the US occurs at lumber and paper mills, where it's a waste product. These facilities use wood waste to provide much of their own steam and electricity needs. Together, these types of wood-burning energy sources form about 20% of the US renewable energy portfolio. Biomass waste is mostly municipal solid waste that is burned in waste-to-energy power plants. Biomass materials accounted for about 64% of the weight of the combustible municipal solid waste and for about 51% of the electricity generated. It is a small component, only about 4% of the U.S. renewable energy portfolio. We'll go into a bit more detail about the 3 other types of biological fuels. Biogas is methane that can come from landfills, wastewater treatment facilities, or from cows. Ethanol comes from fermentation of plant carbohydrates, and biodiesel comes from plant oils. Each of these forms of biological, or modern carbon-based, fuels has its unique features, but all share some common advantages and disadvantages. Biological energy sources have several advantages compared to traditional fossil fuels. They are renewable, and even if fossil fuels run out, we could keep growing plants to be turned into fuel. They typically emit fewer contaminants that produce smog, so less air pollution, and they can be used to lower oil imports if the plants are grown and processed locally. They can also be considered to be carbon neutral, as the carbon dioxide emitted by biomass burning is equal to that removed by photosynthesis when the plants are grown. However, we do need to be careful, because for some biofuels, like corn-based ethanol, if we consider the energy sources used to grow the crop, produce the fuel, and transport it, then the fuel is no longer carbon neutral. Focusing in specifically on the biofuels, ethanol and biodiesel, they also come with challenges. First, they require a lot of land, and the removal and replacement of existing biomass on that land can initially decrease the offset of carbon dioxide associated with converting to biofuels. Second, the energy is needed to convert biomass into fuel, reducing the energy return on investment that can be achieved by biofuels. Third, biomass is less energy dense than gasoline, so you get less energy per volume of fuel. However, this is somewhat offset by more efficient combustion of biofuels. And fourth, food resources can be affected. For example, 40% of the US corn crop in 2011 went toward producing ethanol, which represented only 9.6% of the gasoline consumed in the United States. Because of these challenges, scaling up production of biofuels may be limited. For example, globally, biofuel production doubled between 2006 and 2011, but still accounts for less than 3% of the supply of transportation fuels. The primary problem is that to supply even this limited volume of biofuels, a significant amount of farmland is being used that could have gone toward producing food. Biogas takes advantage of the methane that comes from several kinds of waste: landfills, wastewater treatment plants, and even cow manure. In all of these environments, if solids are broken down anaerobically, in the absence of oxygen, methane gas is released. This methane, or renewable natural gas, can then be burned to produce electricity and heat, or it can be used as a fuel. At landfills, methane gas is vented from underground and can be captured and burned as a fuel. At wastewater treatment plants, biosolids are combined with the right mixture of bacteria to generate methane. For example, biosolids from the city of Akron's wastewater treatment plant are sent to a renewable energy facility across the river. That facility produces enough electricity from the anaerobic digestion process to power itself and almost half the electricity used at the wastewater treatment plant. Farmers can also install anaerobic digesters on their farms because cow manure is 65% methane. For example, a farmer with 50 cows can generate enough biogas for 1/3 of the energy needed to run the farm. The solids left over from the process can be turned into fertilizer or soil amendments. Right now, most of the applications of biogas are fairly small, often providing power mostly for on-site uses. But it is advantageous in taking a waste product, poop, and turning it into energy. That means that little land is required specifically for the production of biogas. On the other hand, let's focus in on bioethanol, the most common biofuel in the US. Bioethanol is produced by large-scale fermentation of plant-derived carbohydrates, which is dominated by corn in the US and sugarcane in Brazil. This requires large amounts of water to solubilize the starch for more complex organic matter and to dilute the alcohol to prevent yeast die-off. The diluted mixture can't be used as fuel, and an energy-intensive distillation step is required. Bioethanol from coarser, less processed biomass may help cut down on the energy needed for ethanol production. Production of bioethanol as a major biofuel began in the United States during the energy crises of the 1970s and early 1980s. This effort required government farm subsidies to be profitable, and those continue to exist. The 1990 Clean Air Act amendment required pollution controls on vehicles and set new air quality standards. Cities began requiring the sale of oxygenated gasoline, which includes bioethanol, since it produces less carbon monoxide and ozone. Despite these requirements, ethanol only accounts for about 10% of US gasoline, and that number has been stable for about the last 10 years. Ethanol production is concentrated in a handful of states, most notably Iowa, where continued support of the industry is also politically popular. Biodiesel produced from plant matter is another potentially carbon-neutral fuel source. Biodiesel is less widely used than ethanol in the US, with about 1/7 of ethanol's production and consumption rates. Plant oils can be derived from peanut, sesame, and canola. Vegetable oils tend to be more viscous than diesel, and they need to be preheated. Biodiesel contains vegetable oils that have been processed to make smaller chained molecules. Advantages of biodiesel include lower air pollution, emissions, compounds with higher flash points which can be transported more safely, and compounds that degrade quicker in case of spills. Challenges are, like bioethanol, these materials have a lower energy yield compared to regular diesel. They are more viscous, more easily oxidized, and degrade more easily, and they are hydrophilic, meaning they can attract water molecules which can corrode engine parts. Additives are used to counteract these less desirable properties. Biodiesel is often blended with petroleum diesel. Each feedstock or source produces different properties. You can see the total U.S. biodiesel feedstock in the image on the right. However, any batch of biofuel may have only some of these components within it. As we consider the potential use of various biofuels in the future, it's important to consider the greenhouse gas emissions that result from their cultivation, production, and transport. This graph from 2007 shows you how many kilograms of carbon dioxide, or its equivalent, are emitted per passenger kilometer of different types of fuels. At the bottom of the graph, you can see the fossil fuels outlined in red. Right above that, you can see various types of biomethane, like the biogas we just talked about. Notice that their emissions are all lower than for fossil fuels. Above methane, you'll see the section on ethanol. Notice how variable those bars are. Some ways of producing ethanol have low carbon footprints, whereas others are comparable to fossil fuels. It also varies with where in the world the crop is grown. In the red box, notice how I've highlighted the high carbon emissions associated with U.S. corn ethanol and the low emissions associated with Brazilian sugarcane ethanol. But the opposite is true if we look at biodiesel on the top of the graph. Emissions associated with soy-based biodiesel are much lower in the US than in Brazil. Below that box, you can see that recycled plant oil-based biodiesel has even lower emissions, again because we are using a waste product. So not all biofuels are created equally, and even one type of biofuel can vary in terms of its environmental impact from place to place, depending on production methods. In summary, biological fuels, including wood and biomass burning, biogas, ethanol, and biodiesel, are renewable, locally available, and less air polluting than petroleum, but they generally have a low energy return on investment, and greenhouse gases depend on what fuel is produced and how and where that happens. Finally, if we want to expand our use of biofuels from purpose-grown crops, there are some pretty significant trade-offs between food and fuel to consider.